All right, everyone. So today, Nanocages in medicine. In this project, we basically used COMSOL multiphysics, which is a simulation software, to determine velocity and pressure profiles for laminar and turbulent flow. So we basically did an analysis of chemical engineering concepts in biomedical technology. My name is Bruno.
And I'm Haneen.
And I'm Maria.
Okay, so the main motivation for the project was a common biomedical technology, which is nanocages. So we learned about this concept in the class, and we were interested to find more about it. So nanocages are basically hollow and porous nanostructures that they serve for the purpose of drug delivery. And drug delivery is a challenge that is facing society nowadays, and people are trying to figure out common ways and more ways to do it. So what we did in this project, we used the idea of nanocages and we designed a similar kind of structure that would also serve for the purpose of drug delivery. So as a group, we designed a different structure, which was a hollow cube, which would deliver medicine in a time consistent basis to the human body. And then we analyzed the fluid flow in the cube, in the cylinders and channels of this cube, and we modeled them using both laminar and turbulent flow. Which brings to the next topic, which we wanted to analyze chemical engineering concepts that are behind biomedical technologies. So we took concepts such as laminar and turbulent flow, which are concepts from transport phenomena with chemical engineering, and we used to get fluid flow and velocity and pressure profiles using COMSOL.
So here we come to the design. This is how our device is looking. Basically, it's just a cube, very simple, and it has channels in it. And we chose to do 9 channels just to get a better distribution of the drug delivery in the body. And these channels don't go all the way on both sides, so this cube is not open on both ends. It's only open on one end. And we also tried to design the channel on its own, and we used cylindrical channels to model laminar flow, and we used truncated cones to model the turbulent flow. So here you can see our parameters, the parameters we used. In the bottom, these are the original parameters that we used to model the whole device, and on the top you can see how that's just an example of of us trying to model one channel. So as you see, we used like L/9 for the radius because we used variety of many different parameters to try to get to the best design.
So for the approach, since all the channels in the cage are identical and the cage is symmetric, studies and results were evaluated for a single channel for simplification. Separate files for both laminar and turbulent flow were designed, and many simulations were performed. We studied the effects from changing the rate at which mass is diffusing into the channels, the velocity of the drug entering the channels, and the type of material. We designed different simulations for glycerol, water, and heptane. First, the physics of laminar flow. These are the questions we use from transport phenomena. In this case, we have a stationary system, so the velocity u is equal to 0, and we use the non-slip boundary condition, which means that the velocity of the fluid is equal to the velocity of the limiting boundary, in this case, the wall of the cylinder or cone, which is equal to 0 for this stationary system. Next, we have the physics of turbulent flow with the K epsilon model, which is the most used model in computational fluid dynamics to simulate turbulent flow conditions. In this case, we have 2 transport variables. We find K and epsilon. The compressor flow is less than 0.3. Turbulence model type is average Navier-Stokes, and the reference pressure is 1 atmosphere. And in this slide, we summarize all the questions we used from the K epsilon model.
So here's the analysis of the results. So this is the velocity profile and velocity field volume profiles for the laminar flow. So basically what that means, so the first figure, you can see that the lines are all straight. which means we got good results because laminar flow is characterized by smooth motion of fluid. So all the fluid should be going in straight direction, which means it's correct. And the second figure shows the velocity field volume, which means that in the wall, in the walls, the velocity is lower, which is represented by the blue color. And we can see that in the middle, it's the red color, which means we have a higher velocity in the center, which is something that we know it's true from transport phenomena topics. So here in this one, we modeled the pressure profile. So we figure out that the pressure is always higher in the inlet. So higher pressure here is meant by the color of red. So this we meant as the inlet for the cylinder, and we got that the higher pressure is in the inlet, which means we got good results because that's also something that we know it's true from literature and transport phenomena concepts. So now for turbulent flow, we also got the velocity profile for turbulent flow, and we got that the red color means the outlet. So we represented here where it's next to the red color to be the outlet, and we also got that the velocity is higher on the outlet, which is also true from concepts that we know. Here, the pressure profile for turbulent flow, we also see that the pressure is always higher in the inlet. So we have orange here, and orange, as you see, is a higher pressure. So we have a higher pressure being represented on the inlet and lower pressure, such as purple, on the outlet of the truncated cone.
So here in the next few slides, we tried to plot a few results from different simulations, from many different simulations that we performed. So here in the first one, we see the inlet mass flow versus the outlet maximum velocity. And there's, as we see, it's a linear relationship. It's they were directly proportional to each other. And so we got, when we tried, when we decrease the mass flow with a factor of 10, we decrease the maximum velocity by a factor of 10 as well. And here we plotted the results from, we plotted inlet velocity versus the outlet maximum velocity, and it's also directly proportional, but there's a factor of 2. So if we increase so that the velocity, the outlet maximum velocity at the end, at the outlet, is double the inlet velocity. So this graph, this here is from when we used different material for the flow. So we used glycerol, water, and heptane. And as we see from the graph, that heptane has the highest velocity. So for the same mass flow at the inlet, heptane had the maximum velocity, followed by water and then glycerol.
So for further work related to simulating fluid flow for drug delivery applications, we would consider analyzing the device as a whole instead of just focusing on the channels where fluid flow takes place. In addition, we consider simulating and analyzing how different types of geometry of the device, as well as the material they are made of, influences on the rate of fluid flow transfer on the body. So that's the end of our presentation. Thank you for watching.